Okay, go ahead.
Okay, I don't see any recording. Have you started recording? Okay. So it's a pleasure to have Shamik Banerjess giving us today's CHEP seminar. So I think Shamik does not need any introduction because he's known to
he was for a long time.
Yeah, and he was also here, and he's actually a frequent visitor to IISc. Of course, he has not managed to visit in the over the last year because of the situation, but we hope that he's going to come back. So yeah, Shamik, take it. So he's going to tell us about MHV, graviton, scattering amplitudes. There's some very excellent work that he's been doing in recent times.
Okay, thank you. So yeah, I think you have already heard at least part of the talk probably, because Sudeep, I think, but let me. So so I'll thank all of you for asking me to give this talk. Okay, so this is talk about the graviton scattering amplitude. And let me start now. Okay, so the thing is that in flat space holography, the dual field theory has to compute the S matrix. Now in flat space, the asymptotic symmetries are infinite dimensional, and they act on the S matrix, and the word identities for these symmetries are the soft theorems. Okay. Now the thing is that since we have an infinite number of symmetries, so it is natural to think that even in the absence of a Lagrangian description, we may be able to say something about the scattering and amplitudes. Okay. So now let me go to the main part of the talk. So this is basically, so first we start with the fact that what we want to do, so that is made easier if you go to if you go from the Fock space to the celestial sphere by methane transformation, and this is essentially this integral transformation where this phi epsilon h bar. So this is a field. This is a local field on the celestial sphere, and this can be written in terms of the standard Fock space creation and annihilation operators by this integral transformation. And the thing is that, so this equation holds only in the massless case. Okay. And the thing is that in this case, what we have done is that the massless, the null momentum p mu, so that can be written in the massless case in this particular form, where this z and z bar, so they are the coordinates on the sphere, and this phi h bar, so the particular property of this integral transformation is that this field, this phi h bar z bar, so that's a primary operator with scaling dimensions h and h bar, where this h and h bar are just so they have the standard form, that is delta plus sigma by 2 and delta minus sigma by 2, where this delta is the conformal dimension of this field phi. So it is the same delta which is there in this integral transformation, and this sigma is essentially the helicity of the massless field. And the main interesting point is that if you do this integral transformation, then this field, so that transforms like a primary operator with this particular scaling dimension under the SL2C, which acts on the celestial sphere as global conformal group. Now this delta is the conformal dimension.
Shamik, you're in plus minus minus or minus plus plus the signature. It's not. Is that correct?
Yeah. So it is the standard. So far it is the standard here. So it is like minus plus plus plus.
Okay, minus plus plus. Okay.
Or say plus. Yeah. So that particular thing. That will not, of course, but sometimes actually it is also useful actually to go to the split signature, which is plus plus minus minus, but that will not really play any role in this talk.
Okay.
But otherwise the signature is the standard one. So I don't need to mention which particular signature I'm working in. Now the fact is that if I write this p mu, when I write this p mu in this particular form, so you can see you have one thing which is minus I z minus z bar. So if the p mu is real, then the thing is that the z and z bar, they are just complex conjugates. But the thing is that we will also actually analytically continue this, where we will treat the z and z bar as independent complex numbers. So that we will do. So in that case, p mu is not necessarily real. If you go back to the Fock space here, actually. Yeah. So is that does this is it clear?
Yes.
Yeah.
Yes. Thank
okay.
you.
Yeah. So let me now go ahead. So we have this particular form of p mu. So as I just said, that we also treat the z and z bar as independent complex numbers, and we also take this delta, which is a conformal dimension, as complex number. Okay, so now let's look at this thing. So once I do this integral transformation, so this gives rise to this integral transformation 3 on the S matrix. So this is a S matrix, and you just do the integral transformation on each of the A's. So the A's are here. So the S matrix will have some number of A's, and you do integral transformation on each of them, and that actually gives you the left hand side. And the interesting point is that if you do this transformation on the S matrix, then under the SL2C transformation, the left hand side, which is this, so that transforms like the correlation function of a conformal field theory on the sphere. So this is the standard transformation law, and this H and H bar, as I said, so they are the conformal dimensions of this field phi H bar. Okay, and this factor, of course, come from this dw dz whole to the power h.
Hi, Shamik, can I interrupt you for a moment? This is Sachin.
Hi. Yeah, sure.
Shamik, I just want to understand what is the sense in which you are allowing P to be complex, P mu to be complex? Maybe this is a very elementary question, but
yes, right.
So maybe you can say a few words about the sense in which P can be complex, P mu.
Yeah, so the sense actually in which I am saying this thing is that if you look at the integral transformation of the S matrix, which is this equation 3, so what one can do is that you first compute this thing. So you know, suppose you know particular, suppose you take a particular S matrix for which these P's are all real, and then you write them in terms of this z bar and omega, and you do this integral transformation, so you get the left hand side, and now you basically analytically continue that as a function of z and z bar.
I mean, is there a situation? Can you remind us of a situation in ordinary QFT calculations where you make this analytic continuation of the P's to complex?
Well, so
I
this
mean,
is
normally, you don't even. I mean, of course, it's a on-mass shell condition that is only for real particles, but
yeah, but I just want to hear. So the if you so this part so the if you look at equation 2, so still the p square that is so the p, if I take the z and z bar just independent complex number, in that case this p is still null. So that condition is not violated in this case.
Okay, but these are
So when you
presumably
compute
moment
this p
of
square, yeah,
actual particles. This is are we not thinking about them as momenta of actual particles or actual I mean, in your case, gravitons, I guess, but even
yeah,
at
exactly.
this
So
elementary
these,
level, you can also apply it to photons.
yeah, right.
So are we not thinking of these as actual photons or gravitons?
Yeah, that we are doing. But the thing is
Okay.
that it is just useful basically to think of Z and Z bar as independent and actually analytically continue in terms of them. And the point is that the last question which you ask actually, so in standard quantum field theory where we see this, so I think in all these bootstrap things, so we always analytically continue in terms of S and T, right? So that continuation we can always do.
That's still a little bit different from making p mu itself complex, right?
Yeah, that's a little bit yeah. But other quantum field theory standard is where you apply the BCFW. The BCFW recursion.
Okay.
So there actually you really take the P's to be complex actually.
Needs to be complex. Okay.
Yeah.
I mean,
So
the only situation that I can think of in ordinary quantum field theory is when you do analytic continuation from Euclidean to Minkowski space using
right.
Osterwalder-Schrader, where you
Uh-huh.
have to use edge of the wedge kind of arguments.
Right.
And but I don't know if so that is the situation I know of, but there, the both the assumptions, the axioms and all are very well stated and completely under control. So I was sort of curious the sense in which you were allowing p mu to become complex, but maybe I mean, you have many other things to say, maybe you can just come back to this point at the end of the talk
Yeah,
if you like.
so this is actually, yeah, but that's an important thing actually. But the thing I can tell you is that if you, yeah, so bootstrap, yeah, so there, of course, we make S and T complex. We can, the other example, which is not really S and T, they are actually working with the P's is the BCFW. So that is one more example where I know
Okay.
things basically work because you take them to be complex actually.
Yeah, but so let
Yeah,
me just
from
say
the
one thing that you
act
should continue after
yeah.
this. But for example, if you do this for QED, then it's just the standard garden variety QED that you are you're not changing the model, right? It's just
No, no,
mass
no,
resolution.
no, 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 no.
And so then it's not some exotic model or some exotic analysis like BC, like this four alphabet
No,
BCFW
no, no.
type of
It's not
thing.
actually,
Theory
and
itself
that's
is a very
precisely what
standard
we want,
theory.
right? Because we want to compute the scattering amplitude in say in this particular thing. So we don't want to change the but the thing is that this analytic continuation is useful. I will say for the time being. So the axiomatic thing that you are saying, I think it is not actually not really understood at that year. But yeah, so we will see that well, it's not yeah, so it will work.
Now we
It
can
is
come back
actually,
to this point after the end, no?
yeah,
At
yeah,
the end.
yeah, we can come back actually.
Yeah, yeah.
Yeah,
So, yeah, please go on.
yeah. Yeah, the other point, yeah, so just I want to mention, since, yeah, I will come back to this point, but the other thing I will mention is that since now, the left-hand side of the, so if you do this integral transformation on S, you get this left-hand side, and that transforms like the correlation function of a conformal field theory on the sphere, or actually basically I'm working on the plane. And the point is that in conformal field theory, typically if you also look at the BPZ, the Z and Z bar, they are treated as independent complex number, and then you at the end you can actually come down to the real slice where Z bar is the complex conjugate of Z. So that is one kind of justification for this actually. Yeah, but we can come back to this actually. So these are the objects. So you can see these correlation functions of these phi's. So these are the objects which we actually want to know. And the thing is that these, so basically we want to compute the left hand side, and then you can do an inverse integral transformation to get the S. Okay. Okay, so now let's look at what kind of word identities are satisfied by these correlation functions on the sphere. Okay, so as we said in the beginning, that the one of the things which is actually kind of standard in this field is that is that the word identities for these symmetries are the same as the soft theorems. Okay. So, okay, so let me start with the subleading soft graviton, and that can be written in this form, where these so these phi's are the ones which we have already introduced, and these S1 plus ZZ bar, so that can be defined in this way, which is defined in equation 6. So it is just you take the delta going to zero and this G delta plus ZZ bar. So that's a positive helicity graviton with conformal dimension delta. So this is the form of the subleading soft graviton theorem on the sphere. So now one can easily check that this S1 plus ZZ bar, so that's a primary operator with conformal dimensions 1 and -1. And the thing is that, so now what we want to do is that we want to cast it in a form in the form of a word identity. And if we want to do that, then it is useful to decompose this S1 plus ZZ bar in this particular way. So we just write this. So basically you expand this S1 plus ZZ bar in powers of Z bar, and this expansion basically stops at Z bar square, because you can see from this subleading soft Graviton theorem that this Z bar actually appears in this term, which is Z bar minus Z bar k square. So the Z bar square is the highest power of Z bar which is there. So we can write it in this form. And then what we can do is that we can substitute this expansion here, and then we can compare the powers of Z bar to get this to get these word identities for J0 and J plus minus 1. So now this has this looks like a more so this is a more standard form of the word identity in a two-dimensional field theory. So we can see that these these three word identities. So we have these three coefficients which are this J, A, Z, and they generate the global SL2C bar transformations. So how do you do this? So you can see that this particular word identity, this J1Z times phi is equal to this. So that is equivalent to the global transformation, which I write as delta plus 1 acting on phi HH bar, and that gives me this. Now we can see that this is essentially the action of L1 bar on this phi field, and similarly the J0, which is this. So this word identity is equivalent to the global transformation on phi, which is this, and this is essentially the action of L0 bar. And then the last one is this, which is J minus 1, and this word identity is the same as delta minus 1 acting on phi, which is D bar of phi, which is the same as the action of L bar minus 1 on phi. Now the thing is that, so now in standard way, suppose let's assume that all the standard things actually work. So what we can do a mode expansion of this JAZ, and those modes we write as JAN. And what this JAN does, so they generate the local SL2C bar transformations of this form. So if A is plus 1, then JAN acting on phi gives me this. Similarly, for A equal to 0 and minus 1, what we get are these two. So you have an extra factor of this Z to the power n, and then one can check that these modes satisfy the algebra, which is this, and this is the standard form of what we can call the SL2C bar coherent algebra. Okay, so this we call the SL2C bar coherent algebra because the for n equal to zero, we get these transformations, which are the global SL2C bar transformations. Okay, so now we can do some standard thing, but let me just say that how this SL2C bar coherent algebra is related to the asymptotic symmetry algebra. And if you want to do it, then it may be useful to think of it as a subalgebra of the algebra of singular diffeomorphisms on the sphere. So what we do is that, so for that So let's consider diffeomorphisms of the form where z goes to z and z bar goes to z bar plus az plus bz times z bar and cz times z bar square, where these functions, now these az, bz and cz, they can have poles. Now the thing is that, so in the literature they actually talk about the smooth diffeomorphisms, but the thing is that if you want to do the, I mean, if you look at the scattering amplitude, then what you will see is that you must have these az, bz and cz as singular, so they can have poles, and so that's an important point. So they can't really be smooth. And so now what we can do is that we can choose a basis of vector fields which generate this diffeomorphism, and they can be written in this form. So j minus 1n, j naught n, and j1n of this form. And then what you can easily check is that the commutator of these vector fields is the same as the SL2C bar algebra which we had here. So this is one way of thinking of this SL2C bar algebra as an asymptotic symmetry algebra. Okay. So now let me go ahead with this. So what we want to now, what now we want to do is that we want to find out the OPE between the plus helicity subleading soft graviton, which is this S1 plus ZZ bar, and the field this phi HH bar. So how does one do it? So suppose I want to find out the OP between this S1 plus ZZ bar, and suppose say phi H1 bar, Z1 bar. So what we do is that we take this subleading soft graviton theorem and expand the right hand side of that in powers of z minus z1 and z bar minus z bar 1. So that's what is here. So if you expand the right hand side in this in powers of z minus z1 and z bar minus z bar 1, then you can write that expansion in this form, where this j1 minus p, j naught minus p, and j minus 1 minus p. So that's a, so those are these differential operators, and they have this particular form, and this can be found easily if you just expand if you just expand the right hand side. And the thing is that there is one more thing, which is that if I can actually write this math, so this currently j1 minus p z1 bar acting on this as j1 minus p phi h1 bar z1 bar. So this is a descendant of this field phi h1 bar, and the correlation function of this descendant with the rest of the fields. So that can be written in this form, and this will play a central role in what we will do actually. Okay. So now, so you can do the rest of the things in this way. So you have j1, j0, and j minus 1, and you have the descendant fields. that is ja minus p phi h1 bar, and the correlation function of these descendant fields with these phi's, they are just they have just this form. So just like, so this is quite standard like from the two-dimensional field theories. So that's what you have to do it, and this is, you can do it in a straightforward way, and that's what you get. Okay, so now what we get is that, so now this equation which we have here, so that can be written in the form of an OP between this S1 plus ZZ bar and which is the subleading soft graviton, and this phi H1 bar Z1 bar. So this OP can now be written in this form. So where these J's, this J1 minus P acting on phi, and similarly this thing. So they are the descendants of phi which were introduced here. So, and this is also actually important, that if you know the OP between this G plus delta ZZ bar and phi H1 bar, and now if you do this thing that you take delta to 0, then what you will get is actually given by this, and we'll see that this is actually an extremely powerful thing which we'll see. Okay, so now we can also define, so if you look at this OPE, from this OPE it follows that you can define a notion of primary fields in this way. So you have JAP acting on phi HH bar is equal to 0 for all P greater than equal to 1, and then you have these more standard ones which come from the global SL2C bar, which are just that L1 bar acting on this phi, L1 bar kills this state phi HH bar, and the L0 bar acting on this phi HH bar is the same as H bar times phi HH bar. So these things just you can get them just from here. So this is quite here. So now let's look at the leading soft graviton, and so the leading soft graviton theorem on the celestial sphere has this particular form where this S plus naught ZZ bar, so that is this object here which is delta going to 1, and then you multiply this G plus delta ZZ bar by delta minus 1, and that gives you this S plus naught ZZ bar. And the point is that you get this kind of these kind of word identities, and this PK. So that acting on phi, what it does is that it increases the conformal dimensions H and H bar, each of them by half. So that's what it does. So it will not change the spin, but the conformal dimension, which is this H plus H bar, that will increase by 1. So that's the role of this P. And now what we can do is that we can cast it in the form of a word identity. So we do the same thing. Here you can see that what we will do is that we will expand this S plus naught ZZ bar in this particular way. So it is an expansion in powers of Z bar, and this actually stops at first power of Z bar, because this soft factor which is here, so that just the highest power of Z bar is just Z bar. So this expansion So the expansion of S naught plus ZZ bar in power sub Z bar has this particular form. And then what you can do is that you can substitute this expansion back into this, and then you can compare powers of Z bar on both sides, and what you get is that P naught Z, if you insert this, so that the correlation function of this P0Z with a bunch of phi's, so that has this form. And similarly the correlation function of P minus 1Z with this bunch of phi's has this particular form. Okay, now so these word identities, so they are equivalent to the infinitesimal global space-time translations of this form, where so p minus 1z, so okay, so this must be so this is actually delta 0, this is delta minus 1, yeah. So this is delta naught, so delta naught acting on this phi hh bar, phi hh bar zz bar, so that gives you this. And these conformal dimensions h and h bar, each of them increase by half. And similarly delta minus 1, so that acting on phi hh bar, that just gives you this. So you don't have any factors of z bar. So these are, so what we have done is you just compute the residue of the pole at z equal to z ksa, and that gives you these global transformations. Okay. Okay, so now what we can do is that we can do the same thing. So we can define.
Can I ask you a question?
Yeah, just go ahead. Yeah.
Simple-minded question. So the way that you were doing the Mellin transform, so delta we are supposed to think of as some kind of a conjugate variable to the energy, right?
Right. Yes, that's what it is actually. Yeah.
So omega. So you were taking delta going to 0. So that would correspond to energy. So there was some operator that you defined where you took delta going to 0.
Right. So that is this subleading of graviton. Yes. So this S1 plus ZZ bar. Yeah.
In terms of the original, yeah. But if I'm thinking in terms of what this is going to tell us about the original
soft fact. So these are the softy actually. So since you have already integrated out the omega,
yes.
So now the softly is in terms of this delta. So but that's what we are doing here.
Variable then. Yeah, but delta going to 0 and not delta going to infinity? I would have thought that energy going to 0 would correspond to delta going to infinity. Is that wrong?
Well, that is not actually how. Well, no, I don't think so. So this actually you can, yeah. So this that does not turn out to be the case actually. So what you get is that basically if you do an expansion around omega equal to zero, and then what you get, and then you get poles in omega, and those actually get translated into these poles in delta actually.
I see.
So what you get is that, yeah, so you get the first thing is that this 1 over omega, and then the order 1 term, and then the powers of here, and those actually get translated into poles of delta, and that's why you can see that we have multiplied by a factor of delta here. So just I want to cancel that pole actually.
Yes. But if I wanted to study
similarly, so just one, yeah. So similarly, Here you can see that I have multiplied by a factor of delta minus 1 because you get a pole at delta equal to 1.
I see.
And those, so these are the soft poles actually.
I see.
You can say.
But suppose I wanted to study the high energy limit, say the Regge limit, or
Yeah.
So let's Regge limit. So what would that correspond to in terms of these deltas?
So that is actually the large delta in some sense.
Okay. I see. Okay. Large.
Yeah. So that is actually, yeah. So that is essentially, so yeah, that is like the large delta limit.
Large delta, but probably fixed sigma. Is it sigma is fixed, or do you know
Yes,
what
sigma
happens?
is fixed. So delta and so delta is h plus h bar, and sigma is just h minus h bar. So the spin, the helicity is fixed.
Helicity is fixed.
The conformal dimension which becomes large.
Okay. And are you able to say something about that limit using this approach?
Well, not yet actually.
Okay.
So that is actually, I think recently this Arkani Hamed and Strominger, and they actually wrote something on this. So that has, I think they discuss these things, but it is not exactly that actually, but something similar to that.
I see. Okay.
Yeah. So in this case, what I will do is, of course, we will get the scattering amplitude, and then of course you can take the whatever you want.
Yeah, so you will get the scattering amplitude as a function of, you can go back to as a function of omega itself. That's what you mean.
Yeah, you can actually, at least in principle, you can. Yeah.
Okay.
Yeah. So that turns out to be the case actually. So basically the structure is that, yeah, so I did not show the, yeah, so I did not show the structure of the scattering amplitude in the main space. So they have all these poles in the conformal dimension, and those are the soft poles actually. So if you do a soft expansion in Fock space, and then if you do a main transformation, then those soft expansion basically gets translated into an expansion where you get poles in the conformal dimension at integer a actually, at integer points on the real line. Yeah.
Okay, thank you.
So that is actually one of the things. So you basically get all these word identities from there. Yeah. Yeah, so that is basically the reason I multiply this by delta minus 1, because I just basically want to pick the residue at the pole where delta is equal to 1. So that is the whole idea. Okay, so this the leading soft theorem, so that gives me the super translation. So now I will talk about that. So what we can do is that we can, in the standard way, we can do a mode expansion for this p naught z and p minus 1 z, and then what we get is pn naught and pn minus 1, and they what they do is that they generate the super translations of this form, where delta n naught phi h bar z bar is, you just multiply this by a factor of z to the power n plus 1. So these are, you can think of them as local space-time translation at null infinity, but you also, the conformal dimensions increase by factors of half. Okay, and the point is that you can compute the algebra of these modes. This is the algebra, and they actually form an abelian algebra, which we know to be the case. So this is quite standard, except that this well, the new thing was this SL2C bar content algebra, which is actually see as the asymptotic symmetry algebra. Okay. So now what we can do is that we can play the same game. Basically, I want to find out the OPE between the leading soft graviton, which is S plus naught ZZ bar into phi, and that has this form. So that can be written in this form. So these are the modes of these. So these are the super translation descendants of these fields phi. And that's what is here. So p minus a naught phi h bar and p minus a minus 1 phi h bar. So they are the super translation descendants, and the OP between s plus naught zz bar and phi has this form. So this is actually, this can be obtained in the same way. So you just expand the right hand side of this soft theorem in powers of z minus z1 and z bar minus z bar 1, and like the way we did here actually. Okay. And then of course we got this in the SL2C bar, and then we wrote it down as the OP. Okay, so now you do the same thing here, and then you can write down the OP in this form. Hello. 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 Hello.
Sorry. It's probably a problem with my computer. Please carry on.
Okay. Yeah. Okay, so now we have these, we also get these things. So these are the correlation functions of these super translation descendants, and they have this form, and they can again be obtained from the soft by expanding the soft fact. Okay. Okay, so what we get is that basically at the end of the day, we have two kinds of algebras. One is this SL2C bar current algebra, and we also have the super translations. But now so this is the definition of the super translation primary. That essentially follows from this. And the thing is that, so now what we have is that we have two algebras. One is this SL2C bar and the super translation, and what one can check is that they actually form a closed algebra of this form. So this is an infinite dimensional Lie algebra. Okay. And the thing is that this is essentially the algebra which gives us the MHV amplitudes. So now the good thing is that these two algebras close, and we have this one. Okay. So what we can, so let me just summarize this thing. So what we had was this algebra we got between JJ, so that is this form, which is the standard form. And then the super translations, they form an abelian algebra, which is this. And now what is the algebra between J and P? So that has this form. Okay, so these define, so this is essentially the symmetry algebra that we will work with. Okay. Okay, so now let me say that why the MHV amplitudes are special. So we consider the tree level scattering amplitudes in GR. Now they have the interesting behavior that if you take the scattering amplitude for all plus, or all plus and 1 minus, then that is 0, and so the first non-zero scattering amplitudes are these MHV amplitudes of this form, which is minus, plus, and the rest are plus. Okay, now this set of amplitudes, so they have this particularly nice feature that if you suppose I make one of the negative helicity graviton soft, and then we have this minus and the rest plus, and if I make one of the minus helicity soft, then due to the soft factorization, what we get is that we get the soft factor into an amplitude of this form. But the point is that since in GR we know that for 3 amplitudes, so this is 0, and that means that there are no negative helicity soft graviton in the MHV sector. Now this greatly simplifies things, because now we know that this set of amplitudes of this form, the MHV amplitude, so they should be completely governed by this SL2C bar current algebra and the super translations of this form, which again form a closed algebra. And that is essentially the thing which is useful for getting the MHV amplitude. Now what we will do is that we will verify this explicitly at the level of the OP. Okay. So now let's do the following thing. So this can be done. So we know that what is the structure of this MHV amplitudes, and what you can do is that you can construct the OP. So you can do that integral transformation. You can go to the sphere, and what you can do is that you can do this OP of this form, say G plus delta ZZ bar and G plus delta 1 Z1 Z1 bar, and that OPE has this structure. So these are the just the first few terms, but you have an infinite number of them. So but the thing is that I just wrote down these terms because these terms are the ones which will give me the scattering amplitudes. Okay. Now what we have shown is that we just show the first few terms, but the thing is that we have computed much more than this, and the thing is that they all factorize, and what we get is these plus some other terms, and that basically says that the OP actually exists on the celestial sphere. Now that's a non-trivial statement, because it's not a priori clear that the OP makes sense in this dual or whatever for population you have. Okay. So now we can see that we have written down all these descendants. So this p minus 2 comma 0 acting on g plus delta. So this is the first term. So this b is the beta function, and these are the so this is the super translation descendant, and we also have this. But now the interesting point is that all these descendants are not linearly independent. Now, how do we see that thing? So now what we do is that we have this particular expansion, the OPE expansion, and now we can make this G plus delta soft. Okay, so how do we do that? So we pick up the contribution from the pole at delta equal to zero, and that gives me this. So this I obtain from this. So you just take this limit on this. Okay, and then but the thing is that we know from the subleading soft graviton theorem that the right hand side must be of this form. So this is what we obtained from the subleading soft graviton theorem. Let me show you this thing. So this is essentially this equation. Sorry, this one. Okay, so once you do this, so what you should obtain is this. Okay, now you use that thing at the level of the OPE, and what you obtain this, but this is not the same as this one. So what you can do, so the first term will match. So that's what we see here. Now the order 1 term will not match, and if they have to match, then this thing has to hold. Similarly, if you look at the order z bar minus z bar 1 term, then you get this term from the OPE, but from the subleading soft graviton theorem, what we get is this. What we should get is this. So you just equate this to this, and then what you obtain is this. So these are essentially the things which show that these descendants are not really independent. So now what we can do is that you can, since these things, these OPs and all these things, they hold for all values of the conformal dimension. So what you can do is that for simplicity, you can shift this delta, and you can shift the delta 1 by 1, and if you use this, then what you can do is that you can write these two relations in this form. Okay, now these are the, so now what we will do is the following thing. So we get these two relations, and what you can do is that you can use them. Okay, you can use them, and then you can write this OPE in terms of the independent descendants, and that has this form. Okay, so now you can see that you have this SL to C bar algebra. The SL to C bar descendants are also there. Okay, and similarly you have both the super translation descendants and the SL to C bar. Okay, so as expected, this is essentially the central, I mean, this is essentially the statement which we made here. The fact that this MHV sector, so the symmetry algebra in this sector is essentially the SL to C bar algebra and the super translations. Okay, and you can see that the OP is actually written in terms of the both the SL to C bar and the super translation descendants, and that is essentially a reflection of that fact. Okay. So now let me show you that how the differential equations are obtained, but I will actually get this. So now the interesting thing is that this of course was not obtained from the symmetry algebra. So what we did was that we computed this OP from the explicit expression for the scattering amplitude, but and then now so at the end we will show that these can be obtained just from this SL2C bar algebra, the SL2C bar into algebra, and the super translations. But before that, let me show you that how they can be turned into the differential equations. So what you can do is that you can take this thing and you can insert it inside an MHV amplitude, and then this becomes this, and where these differential operators have this particular form. So they have already been computed here. For example, they are just this. You can see this p minus 2 comma 0. So that can be obtained from here. Similarly, p minus 2 minus 1. So that is also given here. And similarly, the SL2C bar current algebra. So for that, we also have this. So this is essentially the thing that we have used. Okay. So now, yeah. Okay, so you get this differential equation, and then you have one more, which is this. Actually, this one is the most important one, because you can basically get this from this. So this one, the second one, so that gets translated into this. So here this L minus 1 is del del Z, L bar minus 1 is del del Z bar, and J naught minus 1, p minus 2 minus 1, and p minus 2 comma 0. So they have, so that we already know. So those were the things that I have already talked about. And so you can see that you can get a first order partial differential equation for the MHV amplitude. And these things come more or less in the standard way, but the point is that these are completely new. So these things were not known actually, and the thing is that just by looking at the amplitude, you can't basically say that this complicated equation will hold. So this is one of the use of this as asymptotic symmetries in solving for the scattering amplitudes. Now the thing is that, so how many equations are there? Suppose you have an n point amplitude, and then you have n minus 2 positive helicity graviton, and you get n minus 2 such differential equations for this n point function, and that's what is this. So an n point MHV amplitude containing two negative helicity gravitons. So that satisfied n minus 2 coupled linear differential equations corresponding to n minus 2 positive helicity gravitons. Okay.
Shamik, what is the order of the differential equation? If you try to decouple them, what is the maximum order is there?
Well, so these are fast order because you get just del z and del z bar.
But they're coupled, so if you try to decouple them, it will become higher order, right?
Well, I don't know what how to. Well, suppose I have a 4-point function, then I get two such equations, and I can, well, in the 4-point case, since you can write down all the things in terms of the just two cross ratios, so you basically need only one equation to solve for the 4-point function. So basically you will at the level of 4-point you will be left with just a first order differential equation.
I see.
Because you basically don't need two of them. You can just work with any one of them because it is just one cross ratio.
Okay.
And in the higher point, I think, yeah. Okay, I haven't really thought about it, but yeah, but they are like fast order. So because I mean, you get a single power of del z and del z bar. So each equation is fast order, but then they are, of course, yeah.
So this is more powerful than the conformal quadratic asymmetry, which gives you the second order differential equation.
Yeah, this actually gives you the full thing. So this is more like the two-dimensional conformal field theory, the minimal actually. So in that case, it gives you the full scattering amplitude actually.
And can I ask you? So you're also allowing for arbitrary. So in the language of S matrices, you are allowing for arbitrary exchanges, or are the things limited to massless exchanges only?
Or just only massless things, because the reason is that, so see, up to this point, nothing really depends on which particular theory I have. Okay, but now the thing is that here it is that tree-level scattering amplitude in GR, which gives me these two things, that all plus and all plus 1 minus is not there, and that gives rise to this, that you don't have any negative helicity soft graviton in this MHV sector, and that essentially gives me this thing, that this MHV sector is completely fixed in terms of this SL2C bar and this super translations of this form.
I see.
So it is essentially this equation 42 where this thing basically enters.
I see. So this is going to completely fix the endpoint graviton scattering. Is it tree level?
Yes.
Tree level graviton scattering amplitude generativity.
Yeah.
Okay.
So that's the point actually. So up to the symmetries and all these things, so those will of course not depend on which particular theory I have, but then the point is that what they can do, so that will depend on which particular theory I have.
Okay.
And that is essentially because of this, because at tree level in GR, we have these things that all plus and all plus 1 minus is 0, and then that gives me this thing that I can, so the first non-zero amplitude is R's of this form, and these amplitudes are extremely special because I can't have a soft negative helicity graviton in this case, and so I can have only soft positive helicity, and that tells me, because if you notice, I just wrote down S plus, so I just talked about a positive helicity software. Similarly, in this case also, I have a S plus, and this is good enough only for this this MHV sector in tree-level GR. So that's where the particular content is actually. So that's the whole actually, yeah. But the thing is that once you fix it, then rest of the things are completely fixed in terms of this algebra. So that's the point actually. So now we get all these differential equations.
Sorry, so those were like the initial input that you give to solve the differential equation.
Well, not really an input to the different. Yeah, you can say like that. So if you do it abstractly, okay, the fact that this OP, this G plus delta and G plus delta 1, so this OP can be written, the right hand side can be completely written in terms of the SL2C bar and the super translation descendants. Now that essentially follows from this fact actually, that you don't have a negative helicity soft graviton in this sector. Hello? Hello?
Yeah.
Hello? Hello? Hello?
Yeah, carry on, please. Yeah.
Oh, okay.
Yeah, I got it.
Yeah, so that's the thing. So now actually I will do it abstractly. So there you will see actually, yeah. Yeah, so abstractly in the sense that, so apparently one can say that, okay, we got this OP from the scattering amplitude, and then so basically what do I mean by this? Symmetry algebra fixes the scattering amplitude. So the point is that the symmetry algebra fixes these things, and that we'll now see. So basically, so I mean, we must have, so yeah, it is quite clear that what we have to do is basically, so let's look at this for simplicity, just from the point, simplicity, let's look at the state, which is phi zz bar, okay, which is j1 minus 1, p minus 1 minus 1, and this. Now this relationship that basically makes sense only if this phi zz bar, it's a primary under the extended local symmetry algebra, which in this case is this SL2C bar and the super translations. Now what we have to show is that this structure of phi, so that itself is completely fixed by this algebra, and the point is that that is actually one has to check. So how do we check that? So let's start with the state which is phi 1. So let's take this state, so the first one, okay. Now, so this state has conformal dimensions h plus 3/2 and h bar minus half. And now what we do is that we look for all other descendants with the same conformal dimension, that is h plus descendants of g plus delta, which have the conformal dimension h plus 3/2 and h bar minus half. And then one can actually convince that, well, you can easily convince yourself, I mean, if you look at it for some time, that the only other state with this scaling dimension is essentially this, which is p minus 2 comma 0 acting on g plus delta. Okay, so now what we do is that let's consider the linear combination of this form, which is phi equal to, so I have this state which is phi 1, and then I multiply this phi2 by some unknown number which I call C, and the role of the symmetry algebra is to give me this C. Now the point is that I know that this C must be minus delta minus 1, but the point is that we will see that this is also one can get this C using the extended extended algebra. So what we have to do is that so it is actually easy to check that this phi1 and phi2, so which I have this is phi1, so this descendant is phi1 and this descendant is phi2, and there individually primaries under the Poincare group, that is L1 phi I, L bar, so L1 kills the state phi I for all I equal to 1 to 2. Similarly, L bar 1, and we also have this global translation, global space-time translations, P0 minus 1 and P minus 1. So they both kill these states phi I, where I is equal to 1 and 2. So that means that this phi, it's a primary under the Poincare group. So that means this C, you can't get C if you just focus on the Poincare group. So but now we will see that but now we will get C using the local symmetry, and how to do that. So as we said that there this phi z bar, so that has to be a primary under the extended local symmetry algebra. So we just impose those conditions. So first condition is that this, so this is essentially this condition which we have here, this JAP acting on phi HH bar equal to 0 for all P greater than equal to 1. So we have to apply that condition. Suppose, so you apply that this JAN acting on phi, here phi is this phi 1 plus C phi 2, and then you can easily check using the fact that this G plus delta, it's a primary under the extended algebra, and the symmetry algebra, which is this, that these J1n and J0n, they both of them kill phi. Okay, so what we are left with is J minus 1n, and if I now apply this to phi, and so this must be 0. Now this gives me an equation of this form, and then that gives me C. Okay, I mean, so C is minus delta minus 1, so which is essentially the answer that we have to have. Okay, so we get the C using the local algebra. Now the important point is that the global Poincare invariance does not fix C. Okay, you need this local transformation. So that's the interesting point. And now actually you can check, for example, that this other primary descendant, which is this psi, which we can call psi zz bar, which is this. So that can also be determined in this way. So basically what you do is that you start with a state like psi equal to this, plus you replace all this thing by C1, C2, C3, and then you apply this local condition that this JAN should kill the state psi, and that it gives you the C1, C2, C3, and you essentially get back what you had. So and then once we have these null states or primary descendants, so we can easily get these equations, because This is essentially this equation is essentially that statement. Okay. So in that sense, these amplitudes are completely fixed in terms of this SL2C bar algebra and super translations. Okay. Now this is a very particular case because actually MHV amplitudes are kind of the simplest in that sense. Actually, I mean they have EN. And now the point is that what you can do is that since it's an integral transformation, you can actually write down these differential equations for the Fock space amplitude. And for that, what you have to do is that you have to make these replacements, and I can denote the Fock space amplitude in this way, where this this epsilon is plus minus 1 depending on whether the graviton is outgoing or incoming, and I have this one. So now I can make this a replacement, and so in Fock space these differential equations just become this. So now I have got back the omegas which I integrated out. Now, so that, and this is the standard AS matrix in for the MHV amplitudes. So this is quite standard, but the thing is that these equations, what is not standard is that these equations can now be solved to at least in principle they can be solved to get these AS matrices. Okay. Okay, so I am more or less at the end, and yeah, I think, yeah. So I just want to flash these things. So this is for the gluons actually. So you can write down these differential equations for gluons. So I have denoted by a gluon primary on the celestial sphere by GAHH bar. So A is a Lie algebra index. Okay, and this is standard. So this is the MHV amplitude, and then the differential equation looks like this. Now these first two terms, if you look at the first two terms, so they just look like the Zamolodchikov equations, but the interesting thing is that you get an additional term, which is this third term, which comes from the subleading soft gluon factorization. So that term has to be there. Okay, so yeah, so that is essentially the case for the gluons, and you can also, well, at least in principle, you can solve them to get the gluon amplitudes in the MHV sector. And the interesting point is that you get some things which is extremely similar to the Nisnik-Zamolodchikov equations, except this third term, which essentially says that you have one more factorization, which is the subleading soft gluon. Okay. Okay, so let me now conclude this thing. So what we can see is that these asymptotic symmetries are powerful, and they can constrain the S matrix to a large extent. In fact, the point is that in the MHV sector, you can solve for them, at least in principle. I mean, maybe not in practice. I mean, we don't know actually like how to solve them, but at least you can go get those equations. Now, as I said, that in some simple cases, simpler in the sense that for the MHV amplitude, you can determine them completely. Now an important question is what is unitarity on the celestial sphere, and essentially what I will stop by saying that that it will be useful to know how to combine this with the more conventional ways of doing the S matrix bootstrap, where you have massless particles in as external states. Because in that case, because precisely in those cases, you have all these infinite dimensional symmetry algebras, and they can be extremely constraining. And so that looks like what needs to be done, but well, we don't know right now that how to do it. So that's an active field actually. So I'll just stop here. Thanks for listening.
Confident that this is going to give rise to a lot of new directions of research. So one thing that I wanted to understand is, so it seems like you have got enough number of enough constraints, or all that is needed to actually ask the kind of, or answer to the kind of questions that Shiraz is asking about the proof that at tree level the only sensible amplitudes are what satisfy this classical Regge growth behavior.
Yeah. Hello. Hello.
Yeah, I think I can hear you. It's cut first.
Yeah, sorry, I'm an ISC, so obviously my internet. Yeah.
Just go ahead. Yeah.
No, so I wanted to ask if you feel that you should be able to ask the kind of questions that Shiraz is asking, or answer the kind of questions that Shiraz is asking, but prove it without appealing to the ADS-CFT correspondence or any other thing.
Right. So yes, I mean it's not. Hello.
Yeah. Carry on. Yes.
Yeah. So the point is that it is actually it has. Yeah, I mean, I don't know actually like how to do it right now. So that is one thing we have to think. I mean, we are supposed to think.
Okay. Yeah.
Yeah, because this.
But seems you should,
So that
should
is
be able to answer.
Involved question, of course.
But that isn't a limit. So maybe you should be able to ask. Yeah.
Hello.
Oh, yeah. But yeah. No, I was just making the comment that this is in a particular limit. So
yeah, this is in a particular limit. So this, of course, so the thing I showed, so that of course determines the whole amplitude. And then you can consider different limits. But the point is that in most cases, but Shiraz is asking a question which should be like, he is asking a question which is quite, not just for a specific theory or specific class of amplitudes, for any amplitude, I think any tree level amplitude.
Yeah, but you have differential constraints, general differential constraints, right? I mean,
no,
I thought the point was,
these are only for the MHV actually. Because without MHV, you the point is that so that is the thing that we want to do actually. Now the problem is that if you are not in the MHV sector, then the symmetry algebra is much bigger than this.
I see. Okay.
And the point is that we don't, so still we don't know actually how to work with that. In fact, that algebra has the Hasoro, and the Hasoro algebra is also part of that actually.
I see.
Now that is the master actually, in a sense. So once we are trying to, we are trying for a long time, but so far I mean, we could not do it actually. So like algebra, the kind, I mean, you can write down the algebra, but the thing is that what now one has to do is that see that how this algebra basically plays a role in the AS matrix. Like how does one get it from there? I mean, basically we are,
because if you are asking the general question, it's probably very hard. But Shiraz is interested only in a particular limit, which is the high energy limit. So there, that should lead to some simplifications, I guess.
yeah, actually that is a high energy limit. That is like this large delta. I think. Now in the large delta limit, in the complex, of course, in the complex delta plane.
Yeah.
Now the point is that
yeah, I think these are interesting questions that one should continue thinking.
Symmetry algebra will be playing a role because that symmetry algebra is very big. Like it has all the things.
Yes.
The Virasoro is there, the SL2C bar, SL2C algebra.
Yeah.
So that will play a role.
Yeah.
Now the point is that one thing, another thing which is actually is how to consider the massive exchanges.
Yes.
The exchange of massive thing, because then actually one can try to think about how the scattering amplitudes in string theory and things like that, because they will all have massive exchanges.
That's right. Yes.
But that itself is, well, I mean, those have to be like, well, I mean, it has to.
I understand. Yeah.
It has to be done. Yeah. It's not immediately obvious that.
Yeah, I understand. Okay, great, Shamik. So we should catch up again, you and me, with the.
Yeah. So we can start our standard thing actually.
Yeah.